All right, it's 11:10 now. I think we should start. We will do experiment number 6 today, and so far we used Cadence tools and also we used Quarters. So with the Cadence we did schematic design and simulation, and with Quarters we did VLSI coding and simulation. Today we will combine those two together. That means that we will design a circuit using Verilog code, and we will use Cadence to simulate that code. So let's get started. The main objective of the experiment today is to write a test bench so that we can verify our design. Right? So once we design a circuit, we have to test whether that circuit is functioning or not. And it not only functioning, whether it's functioning properly. So we have to test that circuit. Even when we do hardware, we test the hardware design also, whether the input and output matches together. So that's the objective for uh, for today's experiment, and we will verify the test bench. We will verify the design using a test bench, and the tools that we will use is the Cadence. Skipping to the next slide. So now the question is how we can write a test bench. So in Verilog. So this is the template for the test bench setup. The first line should be module. Module is the keyword. Then we have to write the test bench underscore the design name. The design name can be anything. If we want to test a AND gate, the design name can be AND2 or AND3. If we want to test a encoder, then the design name will be replaced by encoder. Then we have to define the input and we have to define the output. For the test bench, we know that for the input signals, we define those as register. Uh, short, in short, we write it with, and for the output, we define it as where. I think you know the difference between register and wire signal. Next, we have to write the DUT name. DUT means design under test. DUT. So if it is a AND gate, then we can write down AND two. And we know that each logic gate has some input and output, so we have to write down those input and output ports. Next is the initial, then we will begin, and then we have to provide some signal in between end and between begin and end. We have to write down some input signal, and we will provide some known input signal so that we know what is the expected output. So this is the basic format for the test bench. Uh, there are some examples. We will go through it, but this is the basic format of the test bench generation. Now there are some specific command that we have to use in order to generate the test bench or in order to write a test bench code. One of the command is all the commands for test bench will start with $sign. If we want to check the input, we have to use the command monitor. And if we want to check the output, we have to use the command display. And we will see how we can use those two. All right, after the simulation is done, the will be saved in a waveform database. In order to open the waveform database, we have to use this command shm underscore open. That will open the result. So we can check the result. The another command is shm probe. That means that it can, it can we use this command to save the result, because we know in a circuit there are many nodes and voltage, and each of the node will have some voltage value and the current value. So we can save we can save all of them, or sometimes we save only very specific nodes. If there may be 100 nodes, then we may save only 10 nodes. Why do we do that? Because if the circuit is very large, and there are hundreds of thousands of nodes, if we save all the voltage and current for each of the nodes, the result file will become very large. So sometimes in order to save space, and it is very difficult to work with large files. It takes a lot of time to open and close large files. So in order to save time and space in the hard disk, sometimes we save only few nodes, see, or some of the results, not all the results. In order to do that, we can use this SSHM probe. But in our case, because our circuit will be very small, we will save all the signals in the database. Next command is SSHM close. After we are done with checking the result, we should close the database, otherwise it will be open and there is a chance that the file may be corrupt. So we have to, after visualizing or checking the result, we have to close the database. So these are the commands. There are 5 commands that we need to use to write the test bench. There are a few other commands. One of them is finish. As we know that Verilog is just like a programming language, like in C or other programming language. Every statement executes sequentially, one after another. So in C programming language, sometimes we use exit or other exit mostly, or end. That will end the program or simulation. For Verilog or VHDL, we use this command and $ finish. It means end of end of the simulation, or the simulation exits whenever it is executed. In simple terms, this is the end of the simulation command. Another command is just a hashtag. So this sign represents delay. So if we have this kind of command hashtag 5, it means there will be total delay of 5 units. Now if 1 unit is nanosecond, it will represent 5 nanoseconds. So we will frequently use this command hashtag to introduce some delay in the circuit. All right, the next is we will need the software cadence, because we will use the cadence to simulate the Verilog code and test bench. The first example is to construct a 2-input AND gate, and we will write a test bench to verify the functionality for this one. Okay, now in order to do that, we have to log into our cadence account, and then we will launch the cadence. In order to do that, X we need to run xmin first. Our xmin is running. Then we have to use party. So I will use my account, but you have to use your own account. because we are not in the university right now, so it may take some time to execute each of the command. So you have to be patient wherever you are doing it this platform. You have to be really be patient. Okay, so we logged into our system. Alright. So next, what do we need to do? So I will follow this step, and you can do the same. Okay. So we have already logged into our Cadence system using Nautilus. Now we have to go to the directory where we have cds.lib and cshrc. And then we have to create and test underscore mod. So I have cds.new documents. So click right button, create document, and then empty file. Now we can name it as and2.v, and we can use another. We can create another document. That is test underscore mod dot. Now next step is we have to open and build up even how to write the on this time. You can write it by yourself, there's no restriction, but it is easy to copy paste from here, so we can save time. The objective is to learn the procedure, not the not to learn the Vedic code. That's not the objective. The objective of this experiment is to learn the procedure. Okay. So we have and two. Let's wait for a while. I think it may take a minute or so to open this file. In order to open the file, there you can open it by double clicking it, or click the right button and open with gedit. Okay, as I mentioned that we will copy and paste from this code. Okay, I think it looks okay. So just save it, and then you can close it down. All right, next we have to open the second file, that is test.mod. So I noticed one thing that sometimes in this lab manual, the name of this test file is different at different location. Like here we have test.mod mode, and here we have test underscore mod only. So uh, try to follow this whichever name you provided in the file. Just follow that name only. Okay, so now we have to open the test. Similar to the AND gate, the example is given here. So what we will do, we will copy and paste, and then I will explain the test bench to it. So let's first copy and paste. Let's save it. Now let's try to go through this test bench. How do we do this? As I mentioned earlier, the first line should be the module definition. In this particular place, we are calling it as stimulus. Stimulus means providing input. Uh, you have already, I think you have already known this term, stimulus. Stimulus is providing known input. Then the inputs, we know that for the AND gate, input is inputs are A and B, and output is Y. We have to define the inputs as register, so that's why we have reg A B. We can define the output as where Y. Then we have to define the device under test, which is AND gate. If we open, you can see this is AND gate, and we are going to test the AND gate. So that's why we have to write it as AND gate here. If we have, if we use the name like AND two, then we should use AND two here. So which means this name must this name must match with the with this name. Anyway, we will follow our lab manual, and it is AND gate there. So we will use AND gate, and we will also use AND gate. But if we want to use NOR or NAND, we have to use the same name as it is here. It should be the same. These two should be the same. All right. So then we have this device under test definition, and input is A. Inputs are A and B, and output is Y. The next is initial. So we have to initialize the simulation. In order to do that, I think when you copy paste, be careful about this symbols. Sometimes the symbols are not copied properly because of Windows and Linux system. So here we have a dollar sign shm underscore open. Then it should be just like this one. Next, so in order to we use this command to open the database, so we can save our results in the database. Then we have shm underscore probe. It defines the which signals that we want to save. The next command is hashtag 50, which means that we have to wait. The simulation will continue until 50 nanoseconds, and then
স্যার
yes.
স্যার এই যে এস এইচএম প্রভোগ, হ্যাঁ ওটাই বলতে চাচ্ছিলাম স্যার।
Okay. Next line is hashtag 50, means the simulation will run for 50 nanoseconds, then it will finish. It will complete the simulation. After that, it will completing the simulation does not stop the simulation. So completion is one thing and stop is another thing. So it will, which means that the input will change until 50 nanoseconds, then the input will not change anymore. That is that finish, the command finish defines that input will not change anymore. But the simulation will continue until 100 nanoseconds, and then the database will be closed. So these are the definition of how the simulation will run. It does not, this section does not provide any information about input. It only says how long it should run, how what are the parameters it will save, and when it will close. That means that we have to provide, still need to provide the input signals. So the next section will define the input signals. And the syntax is we have to use initial and begin. As you see here, every section should begin with initial and begin. So this input section will also start with initial and begin. First, we will have A is equal to 0 and B is equal to 0. Then it will wait for 10 nanoseconds. Then it will change the input 1 equal to 1, A equal to 1 and B equal to 0, and it will wait for another 10 nanoseconds. After that, the input A will be becomes 1 and B will become 1 also. It will wait for another 10 nanoseconds, and at the end, A will become 0 and B will remain 1 and wait for 10 nanoseconds. So these are the definition of input. So what will be the value of the input and how long that will continue. So that defines this input section. This first section defines how we are going to simulate it, the behavior of the simulation, and this second section will define the input signals. And at the end of the and the last line should be the end module. So initial, begin, and end are pair. So they will come in each section will begin with initial begin and end with end command, like here and here, and the entire test bench will end with end module. Alright. So these are the basic structure of a test bench. So let's go to the next section. Now we have to open the terminal and write the command ssh and source sshRC. When we did our previous experiments, we used to write virtuoso. But today we will use different tools from Cadence, which is called NC Launch. So let's wait for a few minutes. I think it will show up soon. Once we start this tool, we will see this the window like this. I think it's also in the left panel. So we should see this window. All right. What we do need to do next is we have to define our work library. Where is my VLSL lab? You don't have to do it because I don't do the experiment by myself. The previous experiment, I have to create a folder for myself. So that should be VLSL lab. And let me start it again. Okay, now we have it. So this the list in for my case the list may be a little bit different than this one, but at least we have this VLSI lab. Now give me a second. I need to set up something. All right, I think we are ready. You don't have to do all these steps to create VLSI lab because you should have VLSI lab already created in your working directory. So let's start NC launch again. Okay, now we should match the list of the libraries here. We have VLSI lab in the lab menu. We also have VLSI lab for my case, for my working directory here also. And you can see we have VLSI lab here and we also have VLSI lab. Now in this step, once we have NC launch running, we need to select VLSI lab, right click and set as work library. Once you do that, you will see a light bulb here. I don't know if you can see it, but it should be visible in your laptop or computer. So once we start NC launch, we have to select our VLSI underscore lab and set as work library. It means that all our input and output or results will be saved in this directory. Okay, so next step is now we have to once we write the code, we know that any programming language we need to write it. We write the code, then we compile it. Select and do V and then use this button to compile it. And the result of the compilation should be visible here. If there is any red mark, that means there may be some error. So we have to debug the error. But in this case, since we are just copying from it from our test lab manual, there should not be any error. But if you see any error, that will be marked in red, and then you can go back to your code and check what is the error. Next, we have to compile the test bench itself. Now select the test bench and compile that. So the test bench that we have is test underscore mod. Notice here the test bench is only test.b here. As I mentioned earlier, throughout this lab manual, you will see different names for the test bench, but they all means the same file, test bench. Whatever name you use, test underscore mod, test underscore mod, or test.b. Whatever the name may be, it represents the test bench. So select test bench and compile it again, and the result should show up here. Again, we do not have any red mark or error sign here, so the test bench is also compiled. The next step, after we compile the test bench, the result of the compilation file will be saved in this folder. So we have to go there and check whether we have that file or not. Now you can see we have two files, AND gate and stimulus. AND gate and stimulus. Okay. Now we have to select the VLSI underscore dot stimulus, this file. Sorry. Now we have to compile this stimulus file. And in order to do that, we have to use this button. Okay. Now our compilation for this stimulus is done. So what we did first, we compiled the the logic gate. Then we compiled the test bench. After the result for of the compilation of the test bench produced these two files. The result for the compilation of end2 produced end gate, and the result of the compilation of test underscore mod produced stimulus. The next step is to compile stimulus itself. We can do it by selecting stimulus and then press this button, as you can see from here. Okay, so the result of this stimulus should be saved under snapshot. So let me elaborate the snapshot. As you can see, we have a file VLSI underscore lab stimulus colon module. Step number 8, we have to select this file and we have to launch another program that is called the NC launch simulator. So we have to select this one and launch the simulator using this button. We select it, then we use this one. So wait for a few minutes or maybe a minute or so. It will pop up a new window. All right. So we launched a new window. Now we should you should be able to see this window. We have simulator and stimulus, just as in this view. We have a simulator and a stimulus. If we click on stimulus, we will see the signals from the AND gate. Inputs are A and B, output is Y. Just like this one, A, B, and Y. The next step is to open the open the plot window so we can observe the input and output of this AND gate. In order to do that, we have to use this button. We have to use this button. It's here. It will bring up another window, just like this one. Now we can see the input and output A, B, and Y, but we do not see any results here because we have not simulated it yet. We have not completed the simulation yet. So in order to complete the simulation, we have to use this button, the run button. We do that, you can see the circuit is simulated and we can see the results. Now if I don't know whether you can see it or not, see it properly or not. We have signal A, signal B, and signal Y. If you recall, if we go back to the code, It's here. So if you recall that the signals that we provided initially it is 0 0, then 1 0, 1 1, and 0 1. Initially both A and B are 0. If I place my cursor here, you can see they both are 0. Then A, we had A equal to 1, A equal to 1, B equal to 0. You can see A after 10 nanoseconds, A become 1. So initially we had A is equal to 0, B is equal to 0. Then we waited until 10 nanoseconds. There's a 10 nanosecond delay, wait period. So initially A equal to 0, B equal to 0. Then we wait until 10 nanoseconds, and after 10 nanoseconds, A become 1, but B remains 0. So A is 1, B is 0. Then after 10 nanoseconds of that change, that means after total of 20 nanoseconds, A remains 1, B became 1. And we know for AND gate, when both inputs are 1, output is 1. As you can see, A equal to 1, B equal to 1, that means output is 1. Now, after this change, we have to wait for 10 more nanoseconds, that is total of 30 nanoseconds. Then A will become 0, B remains 1. And because one of the input is 1 and one of the input is 0, output becomes 0. Okay? And if I check the total duration of simulation, you will see the simulation ends at 50 nanoseconds. If you recall our code, the simulation will 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 stop at or will complete at 50 will be completed at 50 nanoseconds, right? And then it will finish the simulation. So that's what happened here. The total simulation is for 50 nanoseconds. I don't know you can see it, but when you will do it, you will see you should be able to see it. You can see it from here. At the on the right hand side of this plot, we have the time is 50 nanoseconds. 50 nanoseconds. The simulation was completed after 50 nanoseconds. All right. So let's see what's our next step. So we are done with our initial example. So this is how we can generate a code, generate a Verilog code for the gate, and we can also write a test bench to verify the functionality of that code or that logic gate. So we have to have two files. One of the file should contain the logic gate or the circuit itself, and another file should be the test bench that we will use to verify our circuit. And we have seen the meaning of we have gone through each and every step for this test bench and also the AND gate. AND gate is very very simple here, but the new thing for this experiment was to create the test bench. We have been we went through each and every line, and I think we also matched our results with our simulation code or the test bench code. So before we move on to the next section, any questions so far? All right. If there is no question, we can move to the next section. So there, as we have seen for the Verilog code, We can build a Verilog code in three different ways, right? Data flow, structure, and behavior. Similarly, we can gener- generate a test code in very different way, in many ways. But here, one of the example we have seen, we have already seen an example. This is another example for the same entity. The first line should be modulus, stimulus, defining input, defining output, the name of the gate, DUT, input and output. Now we can define an internal variable in any programming language. Sometimes we create an internal variable to do some operation. So in this case, we can similarly create an internal variable just like this. Now the first section is to define the behavior of the simulation. This is pretty much standard, which, as you can see, this section is exactly identical to the previous code. However, when we will define the input section, there we can do it a little bit differently. In this particular case, you can see the standard coding method is initial begin, and at the very beginning we define a equal to 0, b equal to 0. Next, instead of writing down each and every step, like in this case, we wrote down each and every step with the fixed command. That means a will be equal to 0, 0, b will be equal to 1, 0, a equal to 1, b equal to 0, just like that. But we can do it, change these values by programming. We don't have to write down a 1, 1 or 0 specifically. We can use an internal variable to change these values. And we can use this code just like C code. We can do it for loop starting from I equal to 0, and it will end, it will continue until I is less than 4, and at each step I will be will, the increment of I will be by 1. So initially I equal to 0, we begin it, a and b both will be equal to I, that means ab equal to 0, wait for 10 seconds, then I will be equal to 1, then ab equal to 1. 1 means what? 1 means, remember, this variable is an integer. Integer 1 means in digital. In binary code we have 2-bit binary, it will be 0 1. So that means a will be 0, will be 1 equal to 1. And the next step I will become 2. 2 means in the integer 2 means in binary code it will be 1 0. Then it will be a equal to 1, b equal to 0. And at the third step I will become 3, and 3 means in binary 2-bit binary it will become 1 1. So both a and b will become 1, just like this one. So we can write down the same code with a for loop. So this is just an alternate approach. Why do we do this for loop? Because in this case, in this particular example, we may not have huge benefit. But suppose we have 100 different variables. If I want to write down each and every signal, each and every variation of signal like this, there will be thousands of lines of code. But if we use a for loop, we can do the assignment of this variable, of this value to a and b with only single line. So that is the benefit of using for loop. If we have large number of variables, we can define those variables with only one single statement. But at this point, we may not see that benefit because we have only two variables. Okay, so if you are interested, you can try this approach also. Both of the approach, you should see that both will provide us same results. Now we have two more examples. I think this is 2 to 1 marks, and next is 1D flip-flop. So just like AND 2 gate, we have to uh, write a Verilog code for the logic circuit itself. So in this case, our logic circuit is marks 2, and we know the marks 2 has two input, one selection, and one output. So in this case, selection, because we can define only input or output, this selection will be defined as input. So we have in this particular case, in that respect, we have three inputs A, B, and S, and output is Y. So we have input A, B, S, and output. Okay, I think we have already learned this code always. No matter what is the condition, if we have A, B, and S, then if S equal to the code is if S, Y will be equal to B, else Y equal to A. What does it mean? If S equal to 1, Y will be equal to B. If S equal to 0, Y will be equal to A. I think we have done this code in our previous experiment, but with Quadtrust. Today we will do it in Cadence, but the coding is same. So the next step is to build the test code, test bench. As previously, we have to write the first line is module stimulus, input A, B, and S. Input will be registered, and Y is where our test circuit is marks 2. Then device under test, input and output, ABS input, and Y equal to output. Initial, begin. So this is a block to define the behavior of the simulation, and as you can see, it is exactly identical as the previous test code. Initial, begin, then we open the database, we save the database, we run the simulation for 50 nanoseconds, close the database after 100 nanoseconds. So we can just use the same coding as previous. Now, because the marks and AND gate are not same circuit, so input and output will not be the same. That means the input section will be different in this case. So here what we have here, for the input section, initial, begin, we assign the variable a to a random number. So in binary code, random, we can have only two numbers, 0 or 1. So it can be either 0 or 1. We don't know, because we have not written either 0 or 1 here. So it can be anything, 0 or 1. Similar to that, B will be a random number. That means it will be either 0 or 1. Then we select S equal to 0, wait for 10 nanoseconds. Then we define S equal to 1, and wait for 10 nanoseconds. So when S will be equal to 0, based on this code, if S equal to 0, we will get the output A. When S equal to 1, we will get the output B. So that's the test bench to test a math or 2 to 1 marks circuit. I'm not going to do it because the procedure is same as the AND 2 gate, so you can do it by yourself. But in terms of coding, do you have any question? Okay, if there is no question, let's go to the next uh, example. So we have a D flip flop with asynchronous reset. Okay, so I think from your digital logic course, you are familiar with D flip flop with the reset, asynchronous reset. So What does the D flip-flop do when we have clock high? Then input output is equal to input. When clock is zero, there's the output is equal to the previous stage, previous state. We have already uh, discussed about D flip-flop in our VLSI course, but we have not discussed D flip-flop with asynchronous reset. So let's try to define the asynchronous reset. What is asynchronous reset? So asynchronous reset is an additional input to the D flip-flop when it is high, depending on active low or active high. But when it is active, when the reset is active, no matter what is the clock or the input, output will always be zero. So that is the definition of reset. When reset is active, output will be zero. The input can be 1 or 0, clock can be 1 or 0, does not matter. Output will always be 0. Anytime we make the reset active, output will become 0. Okay. So let's go through the code for the Verilog code for the D flip-flop with asynchronous reset. So we have module, D flip-flop, we have clock, data input, Q is output, and reset is another input. So as you can see, we have input, clock, D, and reset. Output is Q. We have written the code for D flip-flop in our previous lab. So this is almost similar to that. So always at the positive edge of the clock, it will check the reset. If the reset is equal to reset is 1, output will become 0. Or but if the reset is 0, output will be equal to input. Right? As I mentioned earlier, when the reset is active, output will be always 0. There is no other option. But if the reset is not active, then output will be equal to input. So very simple code here. Now let's go to the test bench again. Alright, so again we can write a code module. In this particular case, we name it as DFF underscore T. The name here does not really matter much, but once you name something, you have to remember it because we will be using the same name everywhere. Like for this AND gate, we used the name stimulus. That's why we have this name stimulus here. If we run this test bench, you will see a file called DFF underscore TB here. Okay, so that's why this name is important. Once you define a name, that name becomes important. But at the beginning, you can name it anything. Once you define it, you have to remember the name. Anyway, so the device under test in this case is DFF. We have clock, data input, output, and reset. And the sequence, as you know, sequence must be same: clock, D, Q, and reset. Clock, D, Q, and reset. The first section should be the same: initial, begin. So these are the same. These are same as it is for all the test bench. Now we have to provide the input. So the next section is the input section. At the beginning, we have clock 0, D0, and reset equal to 1. We know once if the reset equal to 1 is equal to 1, Q becomes 1, Q becomes 0. After waiting for 10 nanoseconds, we make the reset 0. That means in this case, if we have clock equal to 1, then the output will become the input, or the output will be equal to the input. After 45 nanoseconds of waiting, the reset is made one again. Then after 5 seconds of waiting, reset is set to 0 again. Now in this particular case, as you can see, clock is on at the beginning, clock is 0, t equal to 0. So but we are changing the reset here. Now the question is, where are we changing the clock? Where are we changing the? We are changing reset and reset only. There is no change of clock and D. So in this particular circuit, clock, when we think about clock, uh, the data is random. As you know, the data can be anything, 1001, etc. etc. But the clock is always 10101010, like this, in this particular sequence. So that means it is forever. Okay. So th- that is the new concept in this example, that we have some input that goes forever. So that means that we have to define something that indicates that this particular signal will go in same sequence forever. So that part is defined in this particular section. Initial, forever, after every 10 nanoseconds, D will become invert of D. So suppose we have D equal to 1, after 10 nanoseconds, it will become inverted D, that means 0. And again, after 10 nanoseconds, D will become inverted D, that means 1. So the input signal D will change after every 10 nanoseconds. It will become 1 0 1 0 and 1. And also the clock will change the similar way. If the clock equal to 1, after 5 nanoseconds, it will become 0. If the clock equal to 0, after 5 nanoseconds, it will become 1. So we have a signal that will continue 1 0 1 0 this sequence forever. If we have any signal that continues in a particular sequence, we can define that signals in this fashion. So if we want to change D after every 10 seconds, we have to write initial forever hashtag 10 D is equal to tilde D. Similarly, for clock, we have to write initial forever hashtag 5 clock is equal to tilde clock. Okay, so this part is new for this test bench. So if we have a forever signal, we can write that forever signal using this syntax: initial forever period, then D is equal to tilde D, or clock is equal to tilde clock. Everything else will remain similar to whatever we have learned so far. Any question? Okay, if there is no question, let's move on. Now here is another example. So initially we had this signal, a specific starting point, and then we can just invert it. In this particular example, what we will do, we, instead of a fixed input, we can uh, change the input data to a random value. Other than that, all the other code should remain same. The only part it will change is here. The data will be assigned randomly. After every 10 nanoseconds, the data will be assigned randomly. Okay. But other than that, everything should remain same. Like this one, clock will change to every 5 seconds to the inverted value. This part should be similar, and this part is also the same. Now let's take a look at the simulation results. So you have to take the results, screenshot of the results for each of the example that we have here today, we discussed today. And then you have to write, for the report task, you have to write the Verilog code for 4 to 1 marks. In today we discussed 2 to 1 marks. You have to write a code for 4 to 1 marks. And then next assignment, and of course you have to simulate it. You have to provide, you have to, in the report you have to include the uh, code for the circuit, you have to include the code for the test bench, and you have to provide the output waveform, the snapshot of the output waveform. That goes for all three. The next one is 1 to 4 demarks. Demarks is just an opposite of marks. I think you already know that. And similar to number one, you have to provide it. You have to submit your uh, code for the circuit and code for the test bench and input and output coefficient. And the last of all is 3 to 8 decoder. Okay. So these are your report tasks, and you have to submit the comment or discussion if you have, if you see anything that is unexpected, anything unusual, or is there any difference between the theoretical value and the simulation value. All right, any question? If not, I think we're done for today. That because we are doing it online, so I don't have any way to check your work for today. So I will rely on your report. So do this, write the code, do the simulation, and provide the result in your lab report. Your lab report will be due next week, uh, before the lab. So let me discuss one more thing, is that our timing, and we have to have some test. There will be some test for this lab. So we have, according to our calendar, we have another class on 27th November and 4th of December, and then 11th and 18th of December. Your final will start from 26th, and 25th is a holiday. So we have four more classes: 27th November, 4th, 11th, and 18th December. So there will be. Can you mute your mic? So there will be test uh, based on the experiments. The dates for the test, lab test, will be announced later. But there will be test from the cadence, there will be test from the quarters, and there will be test from this last few experiments also. The time and the duration will be announced later. Any question?
Sir, the test will be based on which experiments? Experiment 1, 2?
Experiment one, two, three, four.
1
I
to
mean,
4, essentially.
all no, it will
All
be
of them.
all of them. Yeah.
Okay. It's basically the final exam then.
Final midterm all together. Okay.
Okay.
Because
Okay. Noted.
we will cover all the experiments.
Sir, experiment 4 portal is not opened in the classrooms.
Okay, I will open it. Okay, so the due date will be by next week. Okay, done. Any other question? If not, I think we're done for today.
Sir, attendance.
Assalamu alaikum.
Yes,
So there is no circuit here, right? We only need to show the code and the waveform.
yes, for this experiment.
Okay, sir.
Okay, so someone else was trying to say something.
Sir, attendance. No?
Okay, give me a minute. Okay, what is today was experiment 6, right?
Yes, sir.
So, as how many students? I'm not going to call the names, so pay attention and check your serial number. Serial number 1,
স্যার ইজ ইট ফ্রম ট্রিপলি আর এসি স্যার হচ্ছে ডিসপ্লেতে কিছু দেখা যাচ্ছে না নেটওয়ার্ক প্রবলেমের জন্য
is okay. I'll call the name. MD Mahmudul Haq Imam,
ইয়েস স্যার
Rakesh Sarkar, Fahim Abrar, Akib Hussain,
Yes, sir.
Taskia Galiba,
Yes, sir.
MD Nazmul Abedin
Present,
Shihab.
sir.
Okay, since we are done, you can leave after the attendance. Moslema Haq Oishi,
Present, sir.
Sams Firdos Arnav,
Present, sir.
Kamrul Islam Labib,
Present, sir.
uh, Taushik Hussain,
Present, sir.
Mrinmoy Das,
Present, sir.
Mashuk Mohammad Mishra,
Present, sir. Present, sir.
Famida Akhtar Fiza,
Present, sir.
Sabrina Islam, Nahidul Jaman Akib,
Yes, sir.
Tamima Akhtar.
Present, sir.
This spelling is correct?
Sir, Tamima Akhtar AP.
Oh, present. Hasanul Jaman Sujon,
Yes, sir.
Farhan Ahmed Nafis,
Present, sir.
Sir, Sabrina Islam is present. Her mic is not working.
okay, one at a time. Farhan Ahmed Nafis,
Present, sir.
Okay. Now, who is the other person?
Sabrina Islam.
Sir, 18. Yes.
Okay. Next, Anika Anjum,
Yes, sir.
Khondokar Sajid Rahman,
Yes, sir.
Enamul Haq,
Yes, sir.
Mustafa Fayez,
Present, sir.
Tamid Aldin, 0. K. M. Mukhtar Hussain,
Present, sir.
uh, Al Riza Ruhani,
Present, sir.
Sakib Alom,
Sir, yes. Present, sir.
Sak- Anika Binte Aman,
Present, sir.
Chiranjit Das Joy,
Yes, sir.
Fardin Rahman, Toyobuddin
Yes, sir.
Wara,
Present, sir.
Ababil Hussein Fahad,
Present, sir.
Adri Shankar Das,
Present, sir.
Zohara Kamal,
Yes, sir.
Nushin Nawar,
Present, sir.
Soumitra Kumar Sacha,
Present, sir.
uh, Sijapati,
Yes, sir.
Marufa Akhtar,
Present, sir.
Mohammad Amir Kardar, 0. Soyad Firdaus Hossein Shanto.
Present, sir.
Okay. Okay, let me check one more time.